Hi everyone, welcome to the Data Idol Summer School and welcome back to our community who have been following us for the last 5 years. I'd also like to welcome any new members to our community and Data Science Festival. I'm Charlotte and I'm the Operations Manager at Data Idols. The Summer School is a new pilot programme in partnership with the Data Science Festival. It will run live for 3 months so you can learn in real time and pick up new skills from the comfort of your own home. These sessions are designed at an introductory level, ideal for people transitioning into data or for those of you who are starting out your career. Please use the Slack channel if you're watching this session live to chat with other attendees. The link will be in the chat soon. You can also use the channel Data Idol Summer School for any event-related questions, comments or feedback. We would like to also give a massive thank you to all of our partners who have made this event a success, and also for the 400 plus hours it's taken our team to really make this summer school a reality. All of the sessions have been pre-recorded and can be watched back at a later date starting in September. So from September the 1st, we will be emailing you a link to watch all the sessions back. Therefore, you'll be free to watch them at any time, whether you miss anything or if you want to learn at your own pace. Today, we'll be hearing from Miguel Pereira from Plain Data, who will be giving a session on advanced Python libraries for data science. Thank you very much for supporting the Data Science Festival in partnership with Data Idols, and we really hope that you enjoy the session.
Hello, everyone. And welcome to this session about advanced Python packages. My name is Miguel. I work for plaindata.ai, which is a company founded by myself, where essentially my work is data science, especially applied to biomedicine, healthcare, health tech, med tech, in pharma. My background is actually in medicine, but I decided to change careers and become a data scientist because this is way cooler than seeing people in hospitals, and I prefer to treat people using data as opposed to doing 12-hour shifts. And so this is an interesting topic in the sense that it's a bit difficult to define what is beginner versus advanced package. And in that sense, I decided to pick 3 packages. The first of which is by no means advanced. It's actually a relatively a package that you will come across, or you very soon, or have already come across multiple times, but it's essential in the type of use that you do with that package can go from beginner to advanced. It's something that I cannot skip over. And the 2 other packages that we're going to talk about are what I would consider to be fairly advanced uses for, of Python and in data analysis and data science. So in terms of, in terms of outline, so the 3 packages that I just mentioned, and no needs for a drum roll, are Scikit-learn, Tensorflow, and PyTorch Geometric. So I guess everyone has come across Scikit-learn, has used it, or at least heard about it. It's got multiple functions that are very useful for data science. And again, as I said, its use can go from beginner to very advanced, and it's all about how you use it and the amount of functions that you can use in Scikit-learn. The second one is Tensorflow, and with the advent, or more and more, we are starting to use deep learning on top of machine learning methods. In TensorFlow and PyTorch, not PyTorch Geometric, just PyTorch, are 2 of the main packages that you use for that purpose. So if you want to build neural networks, do natural language processing, audio processing, lots of functions that we use in AI, convolutional neural networks, you can use TensorFlow. And to make it a little bit more complex, instead of talking about, for example, PyTorch, which is very similar to TensorFlow, not just in the functions it implements, but also in terms of its syntax, we're going to talk about PyTorch Geometric. And this one I would definitely consider to be a fairly advanced Python package, because it's not only about its capabilities or even the code it implements, but about all the knowledge you need to have in terms of graph neural networks, which expands upon what you really need to know as a basis in terms of neural networks in the general deep learning framework. In terms of structure, so for each package, so essentially 3 packages, and its structure is basically four items that we're going to touch on. We're going to speak about what each package does. the methods that are implemented. So what can you do with it? And we're going to look over code examples on Google Collaboratory. And the idea here is that we can look at some of the code and the syntax. So this is not supposed to be a theoretical lecture. This is the idea here is that you get acquainted with the code and how things are implemented in Python. And to finish, we'll talk about a bit about where to find information and resources. At the very end, I'm also going to talk about 3 packages which I consider to be honorable mentions. They are somewhat advanced packages, but more in the sense that they are not used usually that mainstream, especially the first one that I'll mention when we get there. In terms of goals for this talk, and just before we kick off with the actual content, the idea here is that to give you a taster of each package and its capabilities. I mean, this is we've got a time limited. This is not a workshop or anything. The idea is to give you an idea of what you can do with these things and start working with the code. And so that brings us to our second goal, which is jumpstart your learning, the spark. I find it that sometimes I just need a little push, someone to sort of show me a few things about the code, and now I've got something to start building, to start learning from. And that's what I usually call the spark. So it's just a little push to jumpstart your learning. And the third one is to get comfortable with the documentation interface on official websites. And for that purpose, what I did was literally I took snapshots of some of the parts that you will find on the websites, and so that you can get comfortable with that. Because part of some of the issues sometimes with learning come from the documentation and the way things work on the official websites not being very organized or clear. And once we get comfortable with that, our learning curve gets a lot steeper. And disclaimer, obviously, this does not replace all the hard work. Learning to use these packages takes time, takes hard work, and in the end, nothing replaces you sitting down in front of your computer and writing all the code for yourself, trying to solve all the problems by yourself, because things will break, things will not work. You will have to rerun things 1,000 times until they start working and making sense. So this will not, unfortunately, will not replace that, but hopefully will make that job easier. All right, so to start off, Scikit-learn. And this is the Scikit-learn's main webpage. Scikit-learn is arguably the best tool in Python for machine learning stuff. It's definitely the most inclusive one, and the one that has more functions that and essentially could do at your job as they decide. Is you could almost strictly just use Scikit-learn for all your analysis in Python. Obviously not ideal, but you could literally do that. And it does things from classification, regression, clustering, so you can split it between stuff that's supervised and unsupervised. It implements a lot of methods in a very simple and easy to code syntax, which is something that I find, which is the thing that I find the most useful. So you've got things from SVM, nearest neighbors, random forest, and you've got random forest for both classification and regression. You've got ensemble methods like gradient boost. You also have clustering methods like k-means, for example, or mean shift. And these are just what I call modeling tools. I'm not even mentioning for now the other support tools that you have to work with data before you feed them into this model. In summary, so what does Scikit-learn do? So it's an all-in-one toolbox for machine learning in Python. And it's literally, so if you have a car and you're a car mechanic, your toolbox, the thing that you always go to when you start working on that car is Scikit-learn when it comes to data science in Python, I would say. It's built on top of 3 common packages for used in Python, which are SciPy, NumPy, and matplotlib, meaning that you can apply functions from these packages to the objects that are generated from Scikit-learn. This is particularly useful when you're trying to process the results that you obtain from those packages, or if you want to plot those results into nice visualizations. It also integrates pretty seamlessly with pandas. So whenever most functions, you can just feed them a pandas data frame or a pandas series, and it's fine with that. It doesn't complain. So you don't have to convert things from pandas to NumPy objects, for example. And in terms of things that it does, this is a summary, my personal summary of what it does and all the functions that are in there. So you've got data processing tools. And so in this case, when you need to normalize or scale data, you've got data modeling functions, which are basically your linear regression, your random forest, your SVM. You've got model explainability tools, which essentially once you've built your model and people say, okay, so what are the features that are contributing to these good predictions that we have? And if you want to understand that and break the model down, that it's got those tools in it as well. It's got native plotting support, which is not surprising given that it's built on top of Matplotlib. And so you can use all these objects with Matplotlib. It also has built-in data sets, which is something we'll touch on in a couple of slides. And a very useful feature is the model, what they call model persistence. For me, I like to think of it as just save and load models. So basically you build a model, you train that model on the data that you have, you can save that model and send that to someone else via cloud server, and that person can use the model that you train, or that person, or you can then use that model and set up on a cloud server, which will be used in a production system, for example. And additionally, because Scikit-learn is such a useful and all-inclusive tool, a lot of machine learning tools in Python are actually built on top of Scikit-learn, meaning that they work seamlessly with Scikit-learn, and they just provide you with functions that Scikit-learn doesn't do. So it's basically, you've got Scikit-learn as the core of machine learning in Python, and then you've got things which are add-ons to it. And a couple of examples are Eli5, which is basically a package for model explainability. So it's got better model explainability or it's got, in a way you can consider it's got better model explainability or more functions for that than the native Scikit-learn. Or it's a bit, I don't think we'll be able to see it, but the idea here is that you've got another package which is called Scikit-survival, which is Scikit-learn for survival data. Personally, I think that the lack of time to event outcome models for time to event outcome in Scikit-learn it's potentially its greatest caveat, but that's because I do work a lot with survival data. Some people, or time to event data, some people might not find it that way, but Scikit-survival essentially gives you all those tools in a Scikit-learn manner or framework. All right, in terms of going over some of the functions, so we've got data processing functions, which include data normalization, creation of dummy variables. So when you've got categories 1 to 5, and just splits that column into 5 columns in one hot encoded, which can call one hot encoded or dummy variables, whichever nomenclature you prefer. It also works with missing data imputation. So you can easily do things like k-nearest neighbors, which we'll see in a bit in the code, or you can just use mean. But the point here is that you don't have to implement these things yourself from scratch. You can just use their functions, and it does all that work for you, which is very useful. In terms of pre-processing functions, some of the pre-processing and normalization functions, you can see it does a lot. And this is the actual screenshot from there. And if you go to Scikit-learn, you'll see this. You'll have a short description of what it does. And then you can click on here. This is a link, and it will give you all the arguments that go inside this. Some of them are relatively easy to guess what they do. So like a one-hot encoder basically encodes the categorical features as a one-hot numeric array. And this is, I would say this is obvious. But for example, the standard scalar, which is also obvious, it standardizes features by removing the mean and scaling to unit variance. This is something we will see in a bit as well. But then you also have add dummy feature, which adds a dummy feature, in this case associated with the one-hot encoder. The one thing I personally don't like about this structure, and which hindered my learning, is that it uses alphabetical order. So it goes from binarizer to S, and then it starts again here from A to P, and for functions that don't start with capital letters. But then you've got things like the standard scalars here, and then you've got things like a binarizer. Pardon me, you've got the standard scalar here, robust scalar here, but you've got other scalars like the min-max scalar and the max ABS scalar are in different part of this list. And you've got things that don't matter in the middle. So it sometimes can be a bit misleading and might make it harder to find all the functions that it does. But in the end, if you get used to it, then you'll know how it works. It's just part about being comfortable with the structure they have. All right, so in terms of model training support tools, for me, these are essential. I mean, I couldn't leave without these in Scikit-learn. and perhaps even more so than the models they implement. So things it does is it does the trend test split for you in a very useful and simple way, which we'll see in the code. It also does cross-validation for you, and you can select the number of folds in how the cross-validation is done. You can select k-fold cross-validation, leave one out cross-validation, whatever you want in terms of methods of cross-validation. It implements it mostly in these two functions, which can actually be a bit misleading as well. We will look at cross-val score, but you also have cross-validate, and they're both doing cross-validation. What it does mathematically, it's exactly the same, but the way it's implemented and the way these functions interact with the model objects is slightly different. And so this one does your modeling all in one go, where this one you basically takes it's something that you do outside of the modeling per se. So when I'm doing cross-validation using scikit-learn functions, I usually use this one, which is the one we'll see in the code. And the other thing which is essential for when you're doing machine learning, obviously, is your hyperparameter tuning. I mean, arguably, after data management and putting the data in data management and processing, which are arguably the things that are more time consuming, I would say this is the second thing that's more time consuming. And you need to spend time making your model or finding the right hyperparameters for your model that will work best. And you can either do it by hand, but that's obviously not ideal. And you've got lots of functions for a few functions to do that. I would say the two most important ones are grid search cross-validation, where you basically define the grid of parameters that you want to search, and it does an exhaustive search. The other one is the randomized search, which we will look in the code as well, where you set up your grid and it uses a random algorithm to optimize the search in the parameter space, meaning you don't literally go, it's not as extensive, making it faster, which is also something that's ideal. In terms of data modeling functions, I mean, essentially it implements pretty much all, except for survival, it implements pretty much all models that you can imagine. So it goes through both supervised and unsupervised learning. This is by no means an exhaustive list, but you can do regression in linear models using simple or regularized regression. One word of caution: when you use regression, it looks at the number of features you are including in it, the sample size, and it might do regularized regression automatically. So if you don't want to do regularized regression, you should specify that. And you also do classification, binary or multi-class classification. This is basic, and that's where it implements things like logistic regression, random forest, SVM, gradient boosts, and other similar models. And you've got unsupervised learning, where you can do things like clustering, k-means, and you can do use dimension reduction, like principal component analysis. You can also do t-SNE, and you can also do UMAP, which is sort of a generalization of t-SNE. And you can easily do all of this by using its native functions, which is quite useful. In terms of the built-in data sets, so Scikit-learn has a lot of built-in data sets, some of which are very well known, especially if you work with other software. So for example, in R, you also have the Boston house prices data set. You also have the Iris data set and Diabetes data set from the Pima Indians. And these are what you would say ground data sets that are used in a lot of examples. They split those data sets into toy and real world data sets, where I would say that the toy data sets are mostly useful for tutorials and for learning. It's the sort of thing that you just use to while you're learning. In reality, at your job, you will have the data set that you need to analyze, which will most likely not be one of these. But these are useful for learning first, and also especially with the real world data sets, because these data sets tend to be large. There are also ways of trying to set up your models in your code before the data you really need comes in. So you might use that. It's also an opportunity to try to stress test your models in terms of scalability when you've got a lot of samples. On top of the actual data sets, you've got two things, which are the generated data sets and the functions to load other data sets. The generated data sets, which we'll see in a moment, are not data, but they are basically ways of quickly simulating data. So you can quickly generate classification data for a classification task, for a regression task, for manifold learning, or even for decomposition. And this can be useful if you want to compare, basically, if you want to compare your model the performance of your model against the data you've got with data which was simulated. So instead of you having to simulate all the data by yourself, you've got these quick functions. The other thing is you can also load other data sets. It's got a set of functions which allow you to download larger data sets, which are usually data sets that take a lot more memory space, like images, sound, or text. And so Scikit-learn doesn't have these natively, but it has functions that will fetch that data from their public repositories. In terms of what I just mentioned about the making data, and this is, I find this quite useful when you're trying to see if your model is actually doing something and you just want to compare it with noise. And in this case, so you can use code and say from scikit-learn.datasets. So this is the datasets section of Scikit-learn. You can load Boston. So you load the Boston house price index, and you can easily put that into your feature matrix in your outcome, so the house price. And you can do and if you want to compare this with regression with just noise, you can do Scikit-learn datasets, import make regression, and you just say make regression and samples. In this case, you create 10,000 entries with a standard deviation of 100, and you just set this whatever seed you want. And again, you can do this for classifier, so make classification. And in this case, because your outcome is continuous, you can compare your outcome with this with this feature noise feature matrix, and you can see if your model is doing something, if your X here has got any information that's not here. And just to finalize Scikit-learn, we've got the pipeline command. This one is an interesting one. I personally don't use it that often. I prefer to set up my own functions, but if you are doing something where you've got 2 or 3 Python Scikit-learn functions that you literally do in tandem with and you don't change anything in the middle, you can use the pipeline command where you are summarizing I don't know, like 10 lines of code into a single line of code using the pipeline command. Because this is basically putting in tandem all the data processing and data in model building functions in a single line of code, which is called using the pipeline command. So what you see here is that you can load this breast cancer data set, you've got your X and your Y, you do a train test split, and for that you use the model selection section of Scikit-learn, and get the train test split. You say that you want to split X and Y. And there's another thing here usually for test size, which you can select, and I'll show you that in a moment. And you get your four objects, your X train matrix, your X test matrix, and your Y train outcome, your Y test outcome. And if you, for example, say, okay, I want to train my random forest classifier, but before that, I want to scale all my data using a standard scaler. So you can just say, okay, pipeline, scaler, standard scaler, RF, random forest classifier, and then you do pipe fit, and it applies these 2 functions in tandem to your X train data set. And then after you do that, you can just use the pipe score, and you can assess the model performance using this pipe object. In a way, the pipe object will have inside it the object scaler and the object RF, meaning that after you've done these 2 in tandem, you can still call your RF object and just use that one, or your scalar object and just use that one. So that's the interesting thing about the pipeline command, which is a very powerful command when used, and it can be very convenient at making your code shorter and clearer. All right, so time for the first Collab exercise. I'm going to switch my screen to, one second, to the Collab window, and we've got here the first exercise. So the first exercise is a binary classifier with scikit-learn and TensorFlow. And obviously we're going to speak about this bit first and then go TensorFlow after I talk about TensorFlow. So we're using Google Collab. If you've not used it before, it's very useful. You can link it to your Google Drive account, and all your data files, all the data files you put on there, you store on there can be loaded into your notebook. So instead of it being just a Jupyter notebook that you run on your laptop, you can run this on a Google server. And one of the cool things about Google Collab is that you can use it for free, a GPU, if you haven't done that, or if you don't know that yet, that's very useful, especially while you're doing TensorFlow or PyTorch. Also, if like me, you've got a laptop with a MacBook Pro with the new M1 chip, TensorFlow and PyTorch can be a little difficult to install. And so if you run things on Google Collab, that's not a problem at all. And you can still use GPU power for free without using your own computer power. So the only thing negative about Google Collab, as opposed to, for example, just using a standard Jupyter notebook, if you prefer to use notebooks like I do, is that sometimes you need to install some of the packages. However, things like NumPy, Pandas, these ones here, you don't have to install at all. So in this case, in these notebooks, the only thing we are installing is TensorFlow and PyTorch Geometric. So, okay, so let's start. For this, we're going to use these packages here, obviously, and also scikit-learn as well, which I did run in a second ago. The tools we're going to use are the standard scaler, which is part of the pre-processing. We're going to use the KNN imputer, which is part of the impute section. But again, this is data pre-processing. We're going to use the model selection, and this is useful in this particular case for the cross-validation and for the randomized grid search that we're going to do. And in terms of models themselves, we're going to do a small logistic regression, and we're going to do a gradient boost classifier and a random forest classifier. And in terms of performance metrics, so we've got the metrics class for which we can call the accuracy score and the ROC AUC score. In terms of data, this notebook will be made available to you. And in terms of data, this is a data set that I have that I've created for the purpose of this talk, which is called lung cancer data set. And this is basically a data set where we've got a binary outcome, which is deceased at 2 years. So whether this is patients with lung cancer, whether these patients are alive or dead after 2 years after they're diagnosed with lung cancer. And we've got a few clinical variables, which are age, sex, smoking, histology, and stage. And the rest of the features are just genes. These are around 4,500 genes, and the values here are gene expression values, which have been previously normalized. So these using bioinformatics tools, and that information you can find here once you get hold of the notebook. And the things you need to know is that obviously sex is categorical with 2 options. Smoking is categorical with 3 options where you have former, current, or never. Histology it's also categorical with 3 categories where we've got lung adenocarcinoma, which is LUAD. We've got lung squamous cell carcinoma, which is LUSC, and we also have other, meaning it does not belong to these 2 categories. And we've got RNA-seq gene expression values for these genes, and the data was previously normalized. So this is just a quick snapshot of the data. And the first thing we're going to do is we're going to prepare our data. So again, the first thing we need to do is to select our outcome, which is our Y. So in this case, it's data deceased at 2 years. And we will now create our X matrix. I usually code everything similarly to what it's in scikit-learn to X and Y, at least at the very low level, just before applying the models. And for this particular first bit, we're just going to use age, sex. Oh God, let me put this down here. We're just going to do age, sex, smoking, histology, and stage simple. And so we're going to remove all the genes and just use the critical data. And we're going to get our dummy variables or do one-hot encoding. I personally prefer the pandas get dummies function as opposed to the one-hot encoder by scikit-learn, but you can use either of them. What I recommend is that you always check how it's doing that one-hot encoding. And the reason why I say this is in this particular case, we've got a drop first argument here, which means that when we go to sex, if you don't do drop first true, if you do drop first false, it will create sex male and sex female. So you've got 2 columns for that. So it doesn't consider the other one as being the reference, which is something you don't really need. So you can just remove that column. So if you've got a categorical variable with 5 categories, you just need 4 columns because the other one is just zeros. But again, it comes down to your preference. For smoking, obviously, since we've got 3 categories, we'll have 2 columns. For histology, same thing, three categories, 2 columns. And for stage, we've got 4 categories for stage 1, 2, 3, and 4. And we get here stage 2, 3, and 4, which are one-hot encoded. But again, that in a way depends also on your personal preference. It's not about, there's nothing technical about it, I would say. So now that we've got our dummy variables, what we need to do is we want to scale our data, and we want to impute missing values, which in this case, there are a few missing values along here, which we can explore using pandas, but something that you can do on your own. And I've got this little function that I've created for some of the work that I do, which is quite useful. And it imputes and scales your data. And essentially, and you can choose the number of nearest neighbors, because when it comes to imputation, you are doing the KNN imputer, meaning that you use the data from the 5 closest patients to that patient. So say you're missing something like stage or histology. So say you're missing something like histology. It will take the data from that patient, find the 5 closest patients in terms of the other variables, and use those to compute the value for that patient. The missing value for that patient. And again, you can choose the number of nearest neighbors that you want. In both of these functions, you've got the scalar where your x scalar fit.transform, and you got your x, and you also impute it, and it returns your scaled and imputed data set at the same time. So this is what we're going to do here. And once you do that to your original x, which was a pandas data frame, it actually Scikit-learn turns it into a NumPy array, in this case, a NumPy array of arrays, where each of these lines corresponds to a patient, and it's literally the vector of all the variables. In here, we've got, so the first map, so now that we've got the dummy variables and then the pre-processing with dummy variables or one-hot encoding and scaling imputation, we feel that our data is ready to apply, and let's go and use the model. In terms of modeling, first one, really basic one, we're going to look at logistic regression. And I've thought that it would be interesting to do logistic regression in 2 ways. Even though logistic regression doesn't really change, you could say it's a deterministic algorithm where the numbers you obtain would not vary significantly. Or let me say that again. So if you run logistic regression on the same data, you will not get different results. Sometimes with other methods, because they're stochastic, you might get it even if you run them on the same data. But here, what we're going to do, and it shouldn't vary that much, even when you do cross-validation by changing the data slightly. However, that's what we're going to do here. And so first thing you do, now that you've got your x and your y, and everything's been scaled and imputed, you do your x, you split your data to train a test data set if you are doing a predictive task, and you define your logistic regression object, which is this logreg object. In this case, I said I want a penalty, an L2 penalty, which is probably the main argument of logistic regression. If you don't say anything, actually the L2 penalty is the standard. If you don't want any sort of regularization because you've got 1,000 people and 5 variables, you don't really need any regularization, you need to specify that. So be aware, which is what I mentioned earlier, be aware when you do things like linear models where regularization is present, it's usually the default in Scikit-learn. So if you've created your logreg object here, and now you do a fit, so you fit your object to your training data, and then you can do the predictions. You can use the model object that you've trained and predict on your test set, and this will give you the predictions. And now if you want to analyze the performance of your model, and this is with no cross-validation, as I said, you can go and you can use functions like ROC AUC score and the accuracy score, and you can see how well the real outcome compares to the prediction, to what your model is predicting. In this particular case, if you print this out, you'll see that the ROC AUC score is not great, but that's not strange for this particular example, because you are trying to predict survival at 2 years by including 5 features about people with lung cancer. Remember, we didn't put the gene expression data on here. And your accuracy score in this case is 0.7. And the reason why it's 0.7, it's something that I didn't show you before, but there's a bit of class imbalance here. So in terms of our binary classifier, you need to take into account that accuracy depends also, it varies according to the real proportion of each category that you have. And the truth is that in this particular case, the number of, if you go and look at your Y variable, your outcome, you will see that there's some class imbalance, and we can see that here. So if we do Y dot value counts, oops, and so you can see that only 200 people are alive and 548 are dead at the end of the 2 years, and this is roughly 70%. So which goes in line with, if your accuracy is 70%, yes, it's fine. You're not predicting that all that much, and that's why the AUC score is slightly better. All right, let me just delete that, go back. And so don't be misled by very good accuracy scores, because if there's class imbalance, it may be meaningless. So this is the example without cross-validation. And so now let's go and see what if we do cross-validation. And again, the results will not be, I would say, different. But what I think it's important here is that we look at how it implements cross-validation. So in this particular case, you can use the model selection class in the cross-val score function. And what it does is it takes in your model and you basically say, okay, I've got another object which I haven't trained, which is the log-reg cross-validation, which is again a logistic regression with an L2 penalty. And I want to train this with using the X train and the Y train data sets. And I want to do 10-fold cross-validation. And I will want to use accuracy as my scoring function. So what it's going to do, it's going to split your data set into 10 pieces. It's going to leave one of those pieces out, train the model, and then assess accuracy on the 1/10 of your data set that was left out. And it does this obviously 10 times, leaving 1/10 out. And again, in the output obviously will be 10 values for accuracy according to how it performed that task in the 10 different folds of your cross-validation. So this is the way cross-val score works. And you can see here that on the first one, it was an accuracy of 73%, then 75, 75, 75, then here 71, 73, 71. And this, what you can do then, you can just do NP mean and you get the mean of this. So alternatively, if you want to have an idea of what would be the average accuracy when you do this, you can do NP mean here. And instead of having all those numbers, oops. All right, so it's got verbose. And when you do that, you got 0.712. And there is sometimes, because the data set is not that big and it's using cross-validation, you might get these error messages. But here you will get the average of those measurements, of those 10 measurements, which you've seen before. The good thing about this, though, is that you can have a performance measure for training, but then because you are using the train and the train data sets, once this model, you will have an idea of what you would expect when you use this on the test data. So what happened here was that it trained it on this object, and this object now has been trained, and you can use it on your test set as a validation, but you will know more or less what you would expect in terms of generalizability of this model. Okay, so now that we've seen the logistic regression, I just wanted to add something quickly, which I sometimes do. Like, so instead, you can also use the cross-validation score. Instead of using just one function, I just left here one of the functions that I used. This is not something for us to go over because it's not scikit-learn, it's just my bad code, where we see the cross-validation score. And you can do the same thing with the number of whatever number of folds you want, and the scoring for accuracy and the AUC. In this case, it's doing the mean, as I said. And so once you put your model object here in your X train and your Y train, it will essentially train the model, and it will go and check the accuracy and the ROC AUC, and it will output the accuracy and the AUC for that model. So here we will have for the log, if you do the cross-validation, in this case, the mean is 0.74, and the raw KUC is 0.61, which this is what we get with the cross-validation, the average when you do these cross-validation. All right, so we've looked over a few things. So at this point, we've seen data processing, we've seen the model selection and how cross-validation works, and we've run logistic regression, so a basic linear model with scikit-learn. In addition to that, I wanted to go over two other models that you can use, and which are random forest and gradient boost, again in this classification example, this binary classification example. And on top of that, I wanted to quickly explore the random grid search cross-validation, where you are in more complex models, where you have multiple hyperparameters. You want to know what are the hyperparameters that will maximize the predictive ability of your model. And so what you can do here, in this case, this is set up as a function. Again, not necessarily great code, but it does the job. And this is basically a function that does random forest and GBM, random grid cross-validation. It will take a model name, and you'll see in a second why. Then your X, your Y, in this case, the test size. This is the test size for your train test split, which you'll see here, the test size. Again, if you want to define a random state, you can define it here as well. And a model directory. In this case, the reason why we define a model name in a model directory is because this function will not only train your random forest and your gradient boost and output their performances, but it will also save those models. And these are models that you can then stay on your hard drive, and you can then open, for example, using a different notebook or send to someone. I personally sometimes like to do my training on one notebook, save those models, and then use those models in a separate notebook where I'm doing validation, for example, using a completely different external data set. So in terms of random forest and gradient boost hyperparameters, you need to define your grid and your grid, the grid of parameters that are going to be used in search. And essentially what you need to define a dictionary where the parameter that is taken by the random forest classifier is here set as a key, and the different values that you want are set as a list next to that, associated with that key. So in this case, maximum features, I got auto and log2, number of estimators, 100, 200, 1,000. You can also do max depth or for example, bootstrap true or false. One thing for the purpose of this exercise, I've reduced significantly the number of parameters that are being searched here. I usually try a little bit more of these, especially the number of estimators. Actually, the maximum depth I didn't change, but also the sample split and the sample sleeve. One thing that I strongly advise, if you're doing this, you really need to open Scikit-learn's random forest classifier page, look at all the arguments it takes, and select by yourself what would be the values you want, which ones you want to use, obviously, or to iterate over, and try to select which parameters you think make sense for that. And it's not an easy job, and it's not strictly technical. There's a bit of playing around and a bit of knowledge that you will gain, or a bit of experience in order to select the best ones here. But so however, the way this works here is that you will just set up your object, random forest classifier, and instead of just doing random forest classifier.fit xtrain at ytrain, which is what's on here, you'd first define that your random grid search. And for that, you do model selection and randomized search cross-validation. You give it the estimator, so your model object, the different parameters you want to go over, which is your random grid, the number of iterations, the type of cross-validation you want to do. This is just whether you want to have some output or not in a random state, and the number of jobs. Number of jobs is essentially the number of cores that you use. If you do -1, you're basically saying use all the cores that you have available. If you just one, it will just use one core. If you have 8 cores and you want to use 4, you can select 4. But if you do -1, it says we'll use all the cores that this computer has. So once you've got this is obviously the bit that takes a bit to run, especially if you've got lots of iterations. And I don't usually do 10. I usually do like 1,000. And again, my parameters here are not so. I've got my grid is larger essentially. And once you fit your models using the randomized grid search, you can select, or you can take the best performing one. Since it's doing cross-validation, it will just will leave one out, or k-fold cross-validation, and the model that performed better on the search space will be the one that you can get here as the best estimator. And like every other model, once you've got your best estimator, you can just say .predict, get your x-test, and you get your predictions. And once you've got your prediction, and once you've got this trained model, you can also save it, and that's where joblib is useful. You just say joblib dump my estimator, my model, then model directory, model name, and whatever you're saving with the .joblib extension. For scikit-learn, joblib is usually, I would say, potentially the one that's used most often, but you can also use pickle, which is basically an extension or a better version of joblib, let's say, where you can, which will also allow you to save the model, sometimes occupying less space. So you can use both of them. I tend to use joblib, but there's no particular reason for that, especially because pickle tends to be slightly superior to joblib. So for the gradient boost, essentially there's nothing new here. You can see that in terms of the syntax itself, you will see that you've got your estimator, the randomized grid search as well. Pretty much everything's the same, with the exception that the random grid is different, because the random grid depends on your choices of the parameters of your estimator. And again, you get the best model, predictions, save the model. And to finalize, since this is a function, you can return something if you want. And in this particular case, it's going to return what the random forest and the GBM performance results on the test set. Because if you recall, right in the beginning, you fed the entire data, and it does the train-out split by itself, and then it just here what it's going to do is you've got the predictions and the real values. It's just going to assess the performance. And when you run this, you will get, oh, I didn't run this, or I don't have the output here. It will take a little bit. When you do this, it will give you the performance of this. So, and this is exactly what's on here. Oh no, I did run it. I just didn't put it on here. So when you run the actual function, you select a model name and a model directory, which in this particular case, this is my Google Drive. And because we're running only the clinical features, I said this model, it's just clinical features, and it will run the entire function. And here you can see fitting folds of each of the 10 candidates. And the first one is random forest. The second one will be GBM. And here it will output the results. And you can see that for random forest, the accuracy score, sorry, the area under the curve of the rock, the area under the rock curve is 52. So not completely random, but not fantastic. But in the accuracy is 0.69, which is pretty much similar to what we were expecting, given that around 70% of the people are given the class imbalance. Of course, this is not necessarily, we need to check what the class imbalance was in this test set as well. Not in our overall data set. And the GBM, for example, here is pretty useless. Even though we've done a randomized grid search, it means that GBM here is not a useful model. The accuracy is on point with the class imbalance, and the GBM is just 0.5. In terms of, and now just to finish off the scikit-learn stuff, we've got how to retrieve our SIG models, and we've got the random forest model. You can just do joblib load, and you go to the path in the model name, and you got your joblib file. And what I like about this, and this is just to show you how to get the model, you've got your model here, and you can see all the parameters that were, all the output parameters of this model. And this is basically from what you've obtained as an output of the randomized grid search. And the same thing for the GBM model. And once you've loaded them, which could be in a separate notebook, you can just use them to do predictions on other data sets, for example. Okay, so let's breathe for a second, and I'm just going to switch screen again. And from Collab, just to finish off for scikit-learn, there are lots and lots of tutorials for scikit-learn. So there's no shortage of resources online, especially free or paid for, whatever you prefer, but there's literally no shortage of things. And I've left here a few links for things that I think are useful. I really like the Towards Data Science blog. It's got some very interesting and clear things. And in the end, if none of these please you, you can literally just Google scikit-learn tutorial and there will be no shortage of resources, aside from obviously the original web page, which in itself also has tutorials. All right, so switch gears and now TensorFlow. So now we're starting to get a little bit more advanced when random forest and GBM are no longer difficult and cool models. We can start using more complex things, and one of them we can use TensorFlow to build our neural networks and our deep learning models to build the real AI stuff. And for TensorFlow, so what does it do? So TensorFlow is, and this is literally what's on the GitHub page, is an end-to-end open source platform for machine learning. It has a comprehensive, flexible ecosystem of tools, libraries, and community resources. It lets researchers push state-of-the-art ML and developers easily build and deploy ML-powered applications. So TensorFlow is a bit of a beast in the sense that it allows you to do deep learning mostly, but they actually mentioned machine learning because you can also implement things like linear regression or standard classifiers like we've seen with scikit-learn. But usually because you've got scikit-learn, you go to TensorFlow when you want to do more of the deep learning stuff, even though, note here, scikit-learn also does some neural networks. The other interesting thing about TensorFlow is that, so it's been built by Google, originally by Google. There's lots of resources using Google large data sets that you can use, and TensorFlow in itself can be used by a data scientist at a small company, and that person could be the only data scientist at that company. So what you could call small professional use, but it can go up to deploying large machine learning AI models, which are used in production systems. So it encompasses all things ranging from one thing to the other. So what they say, for example, and if you go to the website, they'll have simple step walkthroughs to solve ML problems with TensorFlow, going from your first neural network using already image processing, and to recommender systems, and to using generative adversarial networks. So just to show you here, as you can see, where you are basically generating data or new data from the data in itself. So what I mean here is that you've got the numbers here, which is likely the MNIST data set. And if you say, it looks at all the fives and classifies them as fives, and then you tell the model, okay, now write a 5, and it will build that 5 for you, which is based on everything it's seen from the way a number 5 looks in handwriting. So that's really cool. In terms of other features, so as I was saying earlier, so TensorFlow can be used at I wouldn't call it a beginner level, because you can use TensorFlow here and do all the machine learning projects or deep learning projects when you're starting to build a model. So the first passes of looking at a data set and trying to build something that an AI, for example, that will be in a production system. But you will go from here, then you can do machine learning models that or deploy them using JavaScript. They also have a lighter TensorFlow Lite, which can be used on mobile applications in smaller devices like Android, iOS, and Raspberry Pi. So this is usually to deploy models in portable devices, or you can have large production systems. But in any case, so that you can get here, you always need to start here. And this is what we're going to focus on today. But also, it's still on what I just mentioned. TensorFlow can be split into three things. The pipeline, or in TensorFlow, can be said to be load and preprocess data, build, train, and reuse models, and again, it will save your model for you, and then deploy the model in whichever way you like, if you're according to your needs and what you're doing at your company. So, however, most of the learning, I would say, if you are now starting, will focus on this part where you are learning how to load and preprocess the data and build and train these models and do smaller deployments, which are not necessarily in production systems. Yeah, which is literally what I was just mentioning before. All right, so what does TensorFlow do? As I said, TensorFlow does regression classification as well. However, because it's basically a library, a Python library that implements statistical models based on the tensor data structures. And tensor data structures are, again, just matrices. It's just the way they are represented in our computers that makes them slightly different. But then again, you can have multi-dimensional matrices, which with more than 3 dimensions. And so that will be, so say you've got a 5-dimension matrix, and that will be a 5-dimension tensor for TensorFlow. And you are not bound by having a 2D matrix as you have in many problems. And many of my problems are 2D matrices just because of the way people collected the data, but TensorFlow does solve that very well at making things, allowing you to capture the complexities in the data by using its better structuring. However, what you're going to focus on with TensorFlow, I guess, will be deep learning. It does essentially these 5 things, which are neural networks, convolutional neural networks, sequence models, GANs, so the general adversarial networks, and reinforcement learning. And so reinforcement learning is, for example, the sort of models you do when you are training a computer to play chess, for example, and the computer will analyze different moves and how those moves were good or bad. And it will learn from those moves and see whether they're positive or negative, and learn how to act in different situations. It's also the same type of approaches that you use for self-driving cars. And again, but also in addition to this, it also does graph neural networks, which we'll talk about later with PyTorch. All right, so let's move to the TensorFlow coding exercise, which is the cooler part, I think. And what we're going to do here is, so we're going to build a simple DNN, or a simple deep neural network, or if you just want to call it neural network or simple neural network, using TensorFlow. And for that, we're going to use the data that the data set that we've just seen. And in this case, if you are using this for the first time in Google Collab, you might have to install TensorFlow. So please run that command if you're looking over the notebook, and you import TensorFlow. Because TensorFlow versions, so TensorFlow 1.x is very different from TensorFlow 2.x. So you want to make sure that you have a 2.x version. The most recent one is 2.5, but anything above 2.2 or 2.3 will not be significantly different from the 2.5. So again, we've got our data. In this case, we're going to consider everything. So instead of just using the critical features, we're going to put everything in. We're going to get our dummy variables. And when you get the dummy variables, the clinical features will be at the end. So we'll have the clinical features one-hot encoded at the end. We've got the genes, all the genes here, and age, because age is a continuous variable, so it doesn't go into the dummy functions. Then you'll have it there. One thing just to add, one thing that I like about the dummies function here is that, and that's why I use it instead of the scikit-learn one, is that it's better at knowing which variables it should turn into dummies or not, as opposed to the scikit-learn one. But that's, again, personal preference. You might find it otherwise. So now, we impute and scale the data. Just make sure that the size of the data set is right. So we've got 4,553 columns here, same thing here, and we've got 740 patients that we had originally. In this particular case, we're just going to write everything, not as a function, just everything as a simple neural network in this particular case. And we do our train test split, which you can see here. Same thing, same syntax. We've got our test size of 25%, so a quarter of the data. And you can see that the shape of our Y data is 561, meaning we've got 561 in our trained data, in the rest in our test data. There's an additional step here, which makes TensorFlow different from scikit-learn, where here our Y-train variable is basically a true-false column, as we've seen, a true-false pandas series, as we've seen before. But for TensorFlow, it doesn't like things which are not numbers. So you need to turn your true-false into a number. That's number one. Second, that number, it has to be a float number, so it doesn't like integers as values in the tensors, and you need to reshape it as well because of the shape. If you see here, the Y-train shape is a 561 array, but no, it doesn't. You don't have a second value here, and it doesn't like that. And because it doesn't like that, you need to specify that, and that's what's written on here. So you need to change your kind of series into a NumPy array, where you map your true false to an integer. So true false goes to 0, 1 or 1, 0. Then you turn your integer into a float, s-type float 32, and then you reshape it this way, which basically is going to add this dimension here. I would say that the hardest part about TensorFlow is making sure that the tensors you are using are in the correct shape and that you are using the right axes when you are doing your neural network. So sometimes it's easy to mix, especially when you're doing convolutions, mix the rows with the columns, and so it ends up doing the convolutions not in the proper manner. So that's the one thing you need to be careful with. Usually, and because TensorFlow is getting smarter and smarter, it will output an error message, and you will have, and if that happens, feel yourself that you are blessed, because if it didn't happen, you would be doing a wrong analysis, and you might fail to realize that you are doing a mistake. Anyway, just a little advice. So now let's build our neural network. So how are we going to build that neural network? First thing is, because TensorFlow sort of creates a session, an interactive session using Keras as the backend, I always do clear sessions. So if I do train a model, if I do train a neural network, get a model trained, and then I want to rerun it, I always clear my session. So I start my code always with this clear session command, and just to make sure that that you're starting from a clean slate. Then in terms of specifying a neural network, you use the TF-Keras models class, and you've got this sequential. And with the model sequential, what you this framework here will essentially allow you to put inside of it all the neural networks that you can think. So you can use this for what we're doing now, which is a simple standard deep neural network. But you can use this for convolutions as well, because essentially this is the sequence. If you think about a neural network where you have all the layers here, the sequential is just this block of all the layers. And what you put in each line within is what the type of layer you want. So here you just do a fully connected dense layer, and with 128 neurons, and you use the activation, and you select your activation function, which is in this case is a TensorFlow neural network ReLU. And same thing for the other 3 layers. And then in this case, you've got a final layer, which is a dense layer with only one neuron. And this one has a sigmoid function. And the reason why it's a sigmoid function is just because we're doing a binary classifier, and sigmoid, you can also use a softmax, but for a standard binary classifier, you can use the sigmoid function, and you always have a single output node or output neuron, which in this case, it's either 0 or 1 according to the classification given by the model. The other thing it allows you to do is you can select dropout between the dense layers, which is something that, because we've got so much data, it usually improves the overfitting, or reduces overfitting, I mean. And you can do dropout layers, and you select the amount of dropout that you want to do at each of the layers. For example, when you're doing convolutions, instead of doing dense, you would have your conv whatever, and you select the type of convolution you want. You can do dropout, and the other thing you can do is also pooling layers. So where you're putting together after the convolution, you can put together the way you are pulling the data can also be specified here, which is not applicable or not necessarily applicable in this scenario. So this is just the basic thing. So you create a model object with whichever design you want. And this is what I like about TensorFlow. You will have a lot of flexibility on this side of things. And then you do model compile. And when you compile your model, you need to select the type of optimization algorithm. In this case, I chose Adam. I would argue it's also the one most frequently used. Then you need to select the loss function. in this case, because it's a binary classification, binary cross entropy is usually the case, and you can also select the type of metrics that you want to have out. With, in this case, binary accuracy and AUC. You can also select things like precision recall. Interestingly, TensorFlow does not do F1 scores, but you can then calculate F1 scores with the other metrics that you have in here. So it doesn't output them natively. Which can be a bit cumbersome sometimes. After you've compiled the model, so basically design the neural network, design the or select how you are going to optimize and analyze your performance, and then you train the model. And for that, you just do a standard model fit, where you put your training data, your validation data, in this case. So here it's considered what we call the test data, the syntax or the way it's written, it calls it validation data. You can select the number of epochs, and you can say Virgo is true, whether you want to have an idea of what's going on during the model, during model training at each epoch, basically. And this is what just what happens, and this runs very quickly. And you can see here, I just did 10 epochs, but even if it's 100, it's very easy to, it runs very fast. And you can see here that you will have the loss function, the binary accuracy in the training set, the AUC in the training set. Then you've got the validation, the loss function in the validation set, the binary accuracy in the validation set, and the validation AUC in the validation test set. And you can see how it evolves over time. And in the end, you can also use your trained model. Once you've done model fit, you can evaluate that model and say, okay, so how does this perform? Just give me the final loss function, AUC, pardon, this would be accuracy and AUC. So if you do model evaluate, what it will output is literally what you have in the final line of your sort of training report. And here you will see that you will have the validation loss, the binary accuracy, and the AUC. And yep, the other thing which we can do as well, and this is very useful when we are training a model or trying to understand what's the best architecture for our neural network, not necessarily when we are moving into production or into a final model, but this is useful when you're starting to build your model, is you can plot the loss during training and the accuracy and the AUC, or whatever measures you use for metrics in your model. In this case, because we're using the accuracy and the AUC, and obviously the loss is something you always have, you can see how the loss behaves during the different epochs. Again, the same thing for accuracy and same thing for the AUC. And this is useful for several reasons, one of which is it allows you to say, okay, perhaps if I run 100 epochs, and then you start seeing that the test accuracy is going down at some point, it means we are overfitting. And so perhaps you don't want to run 100 epochs, you probably just want 50. And that's something that you can easily see when you look at these plots. You can just say, oh, okay, here, I like this at this point. This is a good compromise between overfitting and generalizability. And this is where I want to cut it. And then you can run the model only with those epochs, for example, and stick it there. There are also things that you can do with TensorFlow, which are, for example, when you're doing this, you can say, okay, so run every 10 epochs, save the model. And this is one of the things that it uses, which are callbacks. And callbacks are are already a relatively advanced used for TensorFlow, where the callbacks could do things like, if the validation accuracy drops by 10%, stop. So the number of epochs depends on that. Or you can just say every 10 epochs, save my model. And once you look at this and you say, okay, I'm happy with these 4 epochs, for example, you can just go and keep the model at 4 epochs, which has already been saved and not the other ones, for example. That would be one of the uses. All right, so let's go without further ado, and without boring you too much, we are going to switch over to PyTorch Geometric. But before that, just quickly give you some TensorFlow resources. In terms of resources for TensorFlow, one that I really like is their YouTube channel. So the official TensorFlow YouTube channel, you can find a lot of videos and tutorials. They're usually lengthy videos, like 30 plus minutes, sometimes a couple hours, but there are good tutorials, and you can have both a theoretical overview and a practical application with code on those. For example, even though I'm going to talk about graph neural networks with PyTorch, they also have quite good tutorial videos on that with TensorFlow. So you can use that to learn the theory in the code as well. And also you have also other things for TensorFlow. And one which I personally recommend is the Deep Learning AI TensorFlow course on Coursera. And not just the TensorFlow developer professional certificate, but the Deep Learning AI courses are usually very good for deep learning. But if you want something that's not that's free, you also have, for example, this YouTube video from FreeCodeCamp. And FreeCodeCamp as well, if you go to the website, they've got lots of machine learning resources. In this case, this is a 7-hour course, Python neural networks in TensorFlow. And there's also a TensorFlow tutorial by Tutorials Point, again, for free. All right, so now PyTorch Geometric. So this is a library which I've only started using recently, but it's, I mean, I really like it just because of the problems it solves. I really like the idea behind graph structured data. And so essentially, what is PyTorch Geometric? So it's an extension of PyTorch for geometric deep learning. So PyTorch is just, it's like TensorFlow, but with a slightly different syntax. I would say that personally, my greatest difficulty with PyTorch is that the syntax is so similar to TensorFlow that I sometimes don't know what I'm doing, to be quite honest here. But for GNNs, because what you do is it's different from what you would be doing in TensorFlow, I would say it's a little bit easier. But apparently PyTorch has more market share at the moment than TensorFlow. I think it's essential if you're doing deep learning that you know both, because at some point one will have a feature that you don't have in the other, and some people will use TensorFlow, other people will use PyTorch, and if you know both, you are good to work with all of them. So even though there's redundancy in what they do, there's no, I think there's benefit in knowing both. So as I said, this is for GNN, so for graph neural networks, so geometric deep learning. This is a very hot topic in deep learning at the moment, and most of the papers that are on PyTorch or mentioned by PyTorch have been published from 2017 onwards, and it includes over 40 GNN operators. And so these are basically 40 different papers that were presented at things like NeurIPS or other machine learning conferences, and they support the implementation of these. It's got a lot of benchmark data sets, so roughly more than 100 for sure, which are usually associated with the papers that implement these operators. And it does things like automatic mini batching, and this is a very important feature of PyTorch, which we'll see in a bit. Deterministic and differentiable pooling operators, which we'll see in a moment in the code. And again, like most of deep learning tools, it also does things that allow data transformation, like data augmentation and point sampling. So things like if you want, say you've got, when you're doing image processing, you've got a big photo with a small cat in the middle, and you want to know if you are trying to identify cats, a way to do a data augmentation is that you take smaller frames around the cat, and where the cat is occupying a larger piece of the image. And in a way, you end up having more images, you generate more data, it augments your data just that way. So it does things like that. And it also does point sampling, which would be the opposite, where you're not really trying to augment, you're just trying to locate a frame around the object that you're interested in, for example. In terms of graph structured data, we've got, okay, put this up here. So what is graph structured data? Essentially, forget about data matrices altogether, and you will have something like this. And in graph structured data, you have essentially three things. You've got the dots, which are the nodes. You've got the edges, which are the links between the nodes. And then each of these have attributes and features. So you can have, in this case, we have our nodes have 3 different features. So they can either be blue, green, or yellow. So we've got 3 types of nodes. And the edges in this case have only one edge attribute, which is the black line. But in other cases, you can have edges of, say, different colors. So you can have an edge say, this increases that, this decreases that, or upregulates, downregulates, or A is connected to B. And for example, this is graph structured data is frequently used in things like social networks. So say on Twitter, say John here follows Sally, and this would be an edge going from John to Sally, but then Sally does not necessarily follow John back, so that would be that other edge. Or you can have this person follows that person, or tweeted that someone's tweet. So you can have different edge attributes as well. And the interesting thing about graph structured data is that it allows you to capture a lot more information, because when you have just a 2D matrix, your columns might be interconnected, but you don't capture that information. And the edges are the key to that, and it will give you a lot more information, or capture a lot more of the information in your data set. So, and the other thing is that you can see that graph data is a generalization of other types of structured data, namely images and text, where, for example, images, you can have your pixels, and you say that this pixel here is, which is next to this pixel here into this pixel here. So if this is green on an actual image, then this image, this next pixel will be red-ish until it goes, for example, to white or pink or whatever. Same thing for so the pixels around each other are correlated more than pixels which are far apart. And same thing with text, which is a sequence of words, and you know that there are 2. So for example, there are groups of words which just cannot show up together unless you have really poor English, like myself. So in the case of the graph structured data, you can see that you can capture this information, and you can have that into what seems to be more disorganized, but even though it's more disorganized, it's actually more flexible as well. So see it as a positive thing, and see it as graph neural networks being able to generalize things that convolutional neural networks or sequence models don't really do, or do, but might not do it as well as graph structures. And essentially, as I was saying, so it captures more complex relationships, and it's frequently used in things like this, like biological networks, social networks, communication networks, and knowledge graphs, where knowledge graphs are essentially huge databases of whatever you want. And nodes can range from things. So saying can be people, but at the same time can be organizations, and then you can have relationships between people and organizations, and between organizations themselves. And so in that sense, you can capture a lot of complexity, and that's why I think it's really attractive about that's why I think it's really attractive about graph structured data. In terms of learning on graphs, I only put here. So what can you do? You've got graphs, and what do you want to do with them? Where's the machine learning? Where's the prediction? Where's the what information are you going to derive from that? So the first thing you can do is graph classification. So say each person has a graph. So in this particular example here, let me put this here for a second. In this particular example here, you've got a network of genes, and you've got edges with different attributes, where you have gene D downregulates gene E upregulates gene C, gene B interacts with gene C, and we don't know what sort of anything else about whether it's up or down, they just interact. And then gene A only interacts as only an edge with B, but not with D. And so this could be a graph for a person. And you can have something like that, and each of these genes could have a value assigned to it, like a mutation or a gene expression, or a mutation and gene expression. And you could use each of these graphs at the level of the patients. So say you've got 1,000 patients, you would have 1,000 different graphs, and you could use it to do a classification task like we had before. And this classification would be, is that person going to be dead or alive at the end of 2 years if they have lung cancer? And so it will give you a discrete classification given the nodes and the edges of graph. The other thing you can do, or one thing an example where this sort of graph classification is used is, for example, you have molecules, and molecules can be seen as a graph structure where you have the molecules themselves, the atoms themselves are nodes, and the chemical bonds are edges. And you can model those and try to predict, for example, the effect of that drug by knowing the effect of other similar drugs, like antibiotics, for example. And you will see the headlines of a few major scientific journals saying AI predicts the efficacy of antibiotics. That's essentially what's happening under the hood. The other thing you can do is node classification. So you've got a graph structure. You don't know, so in this case, you don't know if these are genes. So this could be a gene, this could be a protein, this could be a metabolite, something like that, or a carbohydrate. And if you don't know what this one is, by looking at multiple graphs and links between these things, you can try to classify new nodes. So node classification is another one. And the other task you can use it for is for link prediction. So say we have this graph and we want to know, for example, if there's a chance that gene A is connected to gene B, for example. And we can calculate a probability for that and see whether it makes sense to do link prediction at that level. There's other things you can do on graphs, but these are the three main tasks that people usually use them for. All right. Okay, so let's switch over to the Collab exercise. And this one here. So I need, first of all, a disclaimer. So this notebook was not by myself. So the data and not part of the code was not written by myself. This is based on the actual PyTorch Geometric official website, where they have 5 or 6 different Collab notebooks that you can use. And I highly recommend you do so. They're very useful if you're getting into this. And this is one of those 5, and I've just adapted for a few things, but kept some of the images and stuff. So in terms of PyTorch Geometric, you always need to install it on Collab, which is what we're going to do here. And you install Torch Geometric, which is the main library, but then you also need these two so that you can import data sets from PyTorch Geometric. As a little side note, the -q is particularly useful on Collab because it quiets the outputs of just installing stuff, which you don't really need here. In this particular example, we want to do a graph neural network, and again, we're going to perform a graph classification. We're going to perform a classification task, a binary classification, where you have, say, the green molecules in the blue molecules, and you want to say the predictor effects. And for that, this is literally what we're going to do, the molecular property prediction. And we're going to use the TU data sets. So the Dartmouth University has a lot of resources on PyTorch. They've contributed significantly to building it. And as part of that, they have multiple data sets that you can use, and you can import them easily using Python. And in this case, you just import Torch and Torch geometric data sets, the TU data set, where TU data set is actually the repo where multiple data sets are. And your data set here is going to be the MuTag data set. So if you run this, you will see the size of your data set and the number of graphs, number of features, number of classes. This shows you the one entry of the data set, and I'll show you this so that you can understand how the data is structured. Personally, this was this is where I found more resistance to enter or to understand how this was set up. And I'm going to show you a few things about the data object. Bear in mind that these TU data sets are part of an object called data for PyTorch, and that object has different attributes. So if you go and see, we got the MuTag data set called data set. And if you look data set, it says MuTag 188, meaning we've got 188 graphs, which is also on here. These graphs have 7 features and 2 classes. Classes meaning, so this is the number of classes in our binary classifier, meaning that it's a binary classifier. And the number of features is when you have your nodes, it's the number of features of each of your nodes. And this is what we can see here. So if you look at one of the graphs, so out of the 188, I'm going to look at the 10th graph in my data set. And we've got 4 different entries here. We've got the edge attributes, the edge index, the X, and the Y. X is basically the node matrix, where we have 17 nodes and with 7 features for number 10. This is what you can see here. So if this is a molecule, what you can guess is that if it's 17 nodes, we're talking about 17 atoms, and 7 would be the type of atom, one hot encoded, which is what we actually see here. You see, this is basically one hot encoded, meaning that these are all the same. So they could be like carbon or whatever, something like hydrogen, something like oxygen, and they are one hot encoded with these 7 with the 7 length vector.
And so if you look at the edge indexes, you will see that you will have 0 for, so node number 0 is linked to node number 1, node number 0 is also linked to node number 5. And again, here node number 3 goes to, so 3 goes to 2, 4, and 9. And you also have the reciprocal relationship where you have 0 going to 1, or just the same way you had 0, this 0, 1, and then here you have 1, 0. This is not necessarily mandatory because sometimes you can try to consider causality in a graph. So you would have 0 going to 1, but not necessarily 1 going to 0, but that would be a more complex structure. And in addition to that, you have the edge attributes, where here you can see, so the edge attribute is essentially, you've got 38 edges, which is basically the length of each of these. And then those edges have 4 attributes, meaning that they can, it could be something like I said, so it could be like single bond, double bonds. I'm not a chemist, but the type of different, 4 types of chemical bonds that you can have between different atoms. And so when the other thing you, so when you're doing, again, graph GNNs in or any sort of machine learning algorithm, you want to split things into train and test usually. So there's not really a train test split function on PyTorch, at least PyTorch Geometric. And what you do is basically you shuffle your data set and then you select a bunch of entries. So since you have 188 entries overall, in this case, the idea, so the code here is selecting the first 150 for the training in the last 38 to the test data set after you've shuffled it. And as you can see, so you have 150 and 38 for training and test graphs. Another important thing about this, and one, you don't always have to do this because in this particular case, we have multiple graphs. But for example, when you're trying to do node classification or link prediction, sometimes instead of having multiple graphs, you just have one ginormous graph, and you want to learn properties on that graph. So in this case, you wouldn't have multiple graphs, so you don't really need a train test split because you don't have different graphs or different entries, like you have different patients or different molecules here. So that is something important to consider. The other thing which PyTorch does beautifully is batching. I spoke a little bit about it for TensorFlow, where you can train your models in batches, especially when you're doing like large images and large data sets in which each object takes a lot of memory space. You turn things in, learn or do the training in batches. And this is an what PyTorch does. It uses this data loader function, where basically you got your train loader, and you get your train data set, and you get to do batches of 64, and you also shuffle them before doing the batches. And essentially what you see here, what they do is that this train loader does a batch of 64, and in effect, it gets randomly 64 graphs out of the 150, and creates like a big graph with all of these. So it's not the same thing as when you have one graph that you want to learn stuff on, as I said just before, but it will organize your data into one large graph just for memory purposes. So this is just more memory efficient. It's not necessarily, it doesn't necessarily make the analysis that any different. And what you can see here is that if you look at the structure of each of the batches, so you've got 64, 64, 22, just because these sum up to 150, which is the size of your training set. And what you see is that the number of outcome nodes, or the number of, the outcome is now, instead of being length 1, it's as length 64. And same thing for this one, and 22 for this one, because it's smaller. And again, if you also look at the number of nodes, you will also see that the number of nodes here is way more than you had 17. So it doesn't mean that now you have 1,188 atoms. You just put all the atoms in as different nodes in this big graph with 64, corresponding to 64 molecules. Even though it's putting everything together in a single graph, there will not be any contamination, meaning that the graph belonging to one molecule is not really going to be linked in any way to the graph belonging to another molecule. So have that in mind. There's no data shuffling or data mixing occurring at this point. And now on to the juice of the GNNs, which is how to create a GNN model with PyTorch Geometric. So what happens here is that there are essentially 3 steps. And again, this is the text from the tutorial I mentioned. And the first thing is you embed each node by performing multiple rounds of message passing. What message passing is, it's an expression used frequently in GNNs. And what you have is, say you've got a node and its neighbors around it. And the message passing is you use the information from the nodes that are around it, usually the first nodes, and then on a second layer, you can use more of that, a larger neighborhood. And this message passing is the way you summarize the link information around that. And usually you do things like summing up the values of all the neighbors or averaging the values of the neighbors. And the way you do that, those averages and those sums are sometimes weighted according to the type of edge that you have. So that's how you end up creating node embeddings, because basically a node will not be itself without its neighbors. So that's how you take into account the context of a node. And then you aggregate the node embeddings into a unified graph embedding, which is what it's called, the readout layer. And you train a final classifier on the graph embedding, which we're going to see. And this readout layers is basically because you're doing batching, you essentially train in this case, you've got 3 different batches. You are doing the node embeddings at those 3 batches, and you need to summarize those 3 batches into something which is your readout layer, and that's where that's what you will use to perform your prediction. And that's what we're going to see here. So here, what we do is we import the Torch neural network, Torch neural network functional, which has a set of functions, including the optimizers and the nonlinear functions. And in this case, we're going to use graph convolutional GCN, which is GCN is basically a graph convolutional network. This is the GCN conv algorithm or operator. But there are, as I said in the slides, there are 40. It implements 40 operators and perhaps much more at the moment. And this is just about how you compute those embeddings, and which are the neighbor context of each node. This is one of the most basic ones. And in this case, for PyTorch, instead of just building the model as we did before, here we're going to define a class, which is something you can also do with TensorFlow. You define a class, which is your model, and this is your GCN class, where you initialize your model. In this case, it's got 3 convolutions, convolution 1, 2, 3, and it uses the GCN convolutional operator. And you will start with the number of node features, which is you need to make sure that your data set has this as an attribute, or you can just code it by hand if you like. And then you select the number of hidden channels, which are or just hidden units or neurons or nodes in your layers. Same thing here. And at the end, you do a linear. In this particular case, you use a linear output function, which will give you the number of classes. In this case, it's 2 classes for your binary classifier. And in terms of the forward pass over your data, the way it's set up, it's in this case, then you define your forward pass basically. And your forward pass, which is where you obtain your node embeddings, is you do a convolution, you apply ReLU, do a second convolution, you apply ReLU, third convolution, and now you have after the end of this convolution, you have your node embeddings. And from there, you will get your readout layer, where for each batch, which is here, you will essentially pull together the results from each batch, because this is done for each of the 3 batches. And now we need to put together the 3 batches into one, and global mean pool is basically averaging out the this final output, the final embeddings of the 3 batches. That's essentially what it does. And it's one of the most commonly used ones. And now that you have now that you've put your 3 batches together, you can get your, you can apply the linear function so that you can have your classifier. And in this particular case of this model, you also do a little bit of dropout in this 0.5, so 50%, you drop out 50% of your data randomly, so before you get your classifier. Even though we are using a classifier here, so we have this linear output, which is basically just a probability. So between a value between 0 and 1, if it's greater than 0.5, it's rounded up to 1. If it's less than 0.5, it's rounded out to 0. And that's how you get your classification. And so if then you say model equals my GCN class with 64 hidden channels, this is what you have. So you start with 7 features. You get you perform your node embeddings, which will then have 64 features. So your nodes will be mapped to a 64-dimensional space, and then you apply your linear function on the 64 features so that you have 2 features. This bias parameter is basically when you apply the functions, whether you want to have the bias or not. And arguably, you should always leave it as a true, but potentially in other contexts, you can use the false one. So when you train your model, so now that you've set up your model, basically this is just the framework. And now you want to train your model, and you need to, as before, you need to select an optimizer in a performance criterion. And in this case, we're using the Atom optimizer. So you say torch optim Atom model parameters, and you select the learning rate of 0.01, and you use binary cross entropy as your loss function. It's called criterion here, but it's literally just the loss that you are using. Just bear in mind another thing, which is for TensorFlow, you also instead of defining Atom like I did, where you have Atom as a string, there's another notation where you select Atom in a very similar way. So instead of torch, you have TF, and it's something similar to Optim, and you select Atom this way. So in that sense, Torch and PyTorch can have very similar syntaxes. And now you can also define a train function and a test function. And this is when you run your model given the number of epochs. So I think which is different for Torch and TensorFlow is that in TensorFlow, you usually just, when you do model fit and you select the number of epochs, you iterate over the number of epochs, when you select when you do these functions. So you have a training function where you have your train loader. So your train loader is basically the batches. So if you have got 3 batches, so this will be for data in 1 to 3. So you can see here data loader with 3 items, and it trains your model on your data X, data edge index, and data batch. You applies the loss function and gets the gradient, so does the backward pass, and then updates the parameters and goes back up. Same thing for when you do the test. Here, basically, you are essentially saying whether it's correct or not, whether the predictions match the reality, and you do the same for the 3 batches. And you get the output of the model, you get the predictions, and you compare the predictions with the actual results here, and you get the number of correct predictions, basically. And so these are just the functions. So then you train this using this, where you say, train my model for 100 epochs and get the accuracy in the train set, get the accuracy in the test set. And you can also print the epochs, the training accuracy and the test accuracy, which is what you see here. And you'll see these fluctuations for training and test. Bear in mind that sometimes the test accuracy is superior, but we're talking about a relatively small data set, and the test set is only 38 entries. So you will see that at some point you will see some good fluctuations during training, essentially because of that. All right, so enough of code. Obviously, this is a quick overview of these 3 packages, but I wanted you to have an idea and a basis to work from. And in terms of resources for PyTorch Geometric, I only put here things that are on the website. which are the external resources. So this is the part of the this is a screenshot of their website, and you have a lot of external resources. It can be a bit overwhelming, and these are all very recent things, but you have very good tutorials as well. So this one is particularly good, the PyTorch Geometric tutorial. You should also check out Stanford University. You can literally access their PowerPoint slides from their lectures, and it's all for free, and that is quite useful in which is this one, sorry, graph neural networks using PyTorch Geometric. You have talks, and you have slides and Google Collab notebooks. And in no more code for now, but I wanted to give you just 3 honorable mentions in terms of advanced Python packages. One of them is Siuba. This is a relatively recent package, which if you've worked with R, you will know these functions: select, filter, mutate, summarize, and arrange. These are dplyr functions that are used in R, and Siuba brings these to Python, which I think can be very useful if you're when you're trying to select columns and change pandas data frames. The Siuba can be very useful if you're someone who's coming from R and enjoys using dplyr and tidyverse tools. Essentially, what you can do when you use Siuba is you have your data matrix, which is this empty cars data set, and you can use this thing, which is a pipe command, but not the same pipe as scikit-learns, where I say empty cars group by this variable sil, where this underscore here just means take empty cars, the column sil from empty cars, and then summarize, get me the average HP. In this case, it takes the by sil, which I think it's the number of cylinders. I'm not sure about how this data set works. By each of these groups, get the mean of the variable HP. So if you have 3 groups, you will have 3 rows at the end where, as you can see here, so you got 4, 6, and 8, and it gives you the average HP for that car. And you start off with like 50 plus rows. And it essentially brings to Python some very useful summarizing tools from tidyverse. It takes a bit of time to get used to actually implement this in Python. It seems simple, but it's not that simple. But it can be very powerful and save you a lot of time using this instead of Panda's own tools. The other honorable mention is Plotly. So we've talked a little bit about Matplotlib, but personally, when it comes to doing visualizations in Python, I prefer Plotly. And the reason is because it's so flexible. It uses Java, so it's built on Java and allows you to create web-based visualizations. You can do a lot of different chart types with all the applications you can think of, and it's interactive. So very easily you can build your own plot, and you can go and play with it, and things are moving and all of that. And I personally don't, as a user, don't necessarily need that. But when we are engaging with stakeholders and trying to show our point, telling the story behind our data and our analysis, this can be very interesting and can be a very good strategy to make them interested and make them understand what's going on. And so to finish, we will have it has Jupyter Notebook and Jupyter Lab support, and you can also use it in PyCharm or export it to PDFs. And it does charts like this, like basic charts, statistical, scientific charts. And alongside Plotly, and it's the same set of tools, you have Dash. Dash if you know Shiny, that's Shiny in R, you know this is Shiny for Python. And they claim it's the most downloaded trusted Python framework for building ML and data science web apps. And it's Java-based, and it allows you to create nice apps which people can use to interact. So you can not only put your visualizations, but put our data in, and it's particularly useful for stakeholders. And they have this app gallery where you can see, you can select multiple apps and you can see their code. So you can see the apps, see their code, and it's very useful to learn. Same again here. So this is stuff for finance. You have T-SNE Explorer. I've personally used this one. It's really interesting. We have a Forex web trader. And yeah, so I hope you've enjoyed this talk. I think we've went over what are some of the advanced packages, not necessarily in the most advanced use, but in order to start using them in an advanced way, we got to start somewhere. So I'm Miguel. So I'm working at Plain Data AI, and I'm really interested in working with medical data sets, and also if you are starting off your career and are interested in AI applications in medicine, be in touch, because we might have some interesting projects for you to work on. So that's all. Thank you very much for your attention.